motion of a magnet or a coil, and this is a more and more complicated design of the energy harvester itself. Then I will shift over to piezoelectric conversion, and here you can see a typical piezoelectric converting device. These are typical piezoelectric beams. We have 3 beams over there, and they can position in water but also in air. And by a flowing media across the beam, you can force the beams to oscillate, and this oscillation can be used to generate electricity. The electricity which has been achieved with these devices are shown over there. And this is another piezoelectric conversion principle. Here you can see in the middle of the pipe some typical beams. The beams are in the middle of the pipe, and here outside the pipe. And these beams are generating as well a little bit of electricity due to the vibration of the beams, which is induced by the flow. The typical demand of that was about 1 watt, and they have achieved 3.3 milliwatts, and the power density is relatively high due to the small size of the devices. It's 190 milliwatts per cubic centimeter. This is another typical flatting valve which has a piezoelectric conversion, and here you have an airflow coming from the front, and the airflow makes movement up and down, and the piezoelectric beam is colored in brown, and the brown beam moves up and down and oscillates and generates electricity a little bit. The electricity over here is about 40 milliwatts for an airspeed of about 26 meters per second, which is relatively high. This is a small device, relatively small, which is called a microstructured energy harvester, and it consists of PZT as a piezoelectric material, and the power density is in the range of about 6 milliwatts per cubic centimeter up to 10 milliwatts per cubic centimeter, depending on the mode of operation. And this is the last one, which shows you a typical device in operation. It moves up and down because it's mounted on a shaker, and due to the oscillation you can generate something of energy, and the energy density is shown again. It's in a range of about 1.6 milliwatt per cubic centimeter. Furthermore, for the piezoelectric conversion, there exists a lot of basic construction units which are more and more complicated. So you have the starting with a single degree of freedom device, as you can see over here, and it goes up to about a 6 degree of freedom device, which is more and more complicated. And on the other hand, it's really very expensive to build up such a device. So you have also the combination of magneto and piezoelectric. It delivers a certain amount of energy, as you can see over here. It's not that much, it's about 4.7 microwatt per cubic centimeter, or it's an electroactive polymer conversion, which is also used, and the piezoelectric polymers are used in a vibration mode as well, and the power density is 600 nanowatts per cubic centimeter. And furthermore, you have a magnetostrictive electric conversion principle, which is also very interesting. It delivers a power density of about 7.6 milliwatt per cubic centimeter, but unfortunately it uses galvanol, which is not really cheap as a basic material. And you can find also acousto-electric conversion, and some people are trying to use the radiation from the phone companies to convert it into electricity. There exists a lot of different ideas for converting energy. Here you can see the typical energy density. It's in a range of 0.002 nanowatts per cubic centimeter, which is not really very much. Piezoelectric are also used, but they don't deliver that much of energy as you can see it over here. Nevertheless, if we are looking to the power densities of energy harvesting devices, then we can distinguish between the different principles, and I have only a few of them. The most important one, and this is piezoelectric, which has a power density of above 190,000 microwatts per cubic centimeter, magnetostrictive, magnetoelectric, thermoelectric, and pyroelectric. All the others are below them, so we are in a range which is not really in a high level in comparison to typical generators. If we are considering the literature, then we can see there exists more than 1 million publications about energy harvesting, and it's not possible to manage all of them because many of them have different types of test conditions. It's not clear to find a separation between energy and power, and it's really hard to manage all these devices. The only thing what you can see is many of them are vibration based. Vibration seems to be one of the most waste energy kinds which can be used as energy harvesting basis. But if you are going to use the vibration, you need something like a power adjustment. Power adjustment is that what is known in the field of electrical engineering. If you have a generator of electrical energy and you have a consumer of electrical energy, then both of the devices require a certain amount of energy. And this certain amount of energy is in the best way if the generator and the consumer consume the same amount of energy. That means 50% goes to the generator, 50% goes to the consumer. And this is called the power adjustment. In other cases, you have a bad efficiency of the power transport from the generator to the consumer. And the best case is that what energy harvesting needs to have. In reality, we have the situation if we have vibration-based energy harvesters that the impedance of the consumer is normally constant, while the vibration have different frequencies, so the impedance can change. And if we have a changing impedance, we have a mismatch, and this reduces the transfer efficiency. And therefore, a power adjustment is required, or we need additional electronics. This additional electronic for power adjustment is called SSHI, which is named synchronized switch harvesting on insulator. So you don't take the energy from the harvester immediately or all the time. You take it when the harvester shows the highest value or the amplitude of the voltage. So there exist some different types of electronics, as you can see over here. And the difference is shown over here. Here you can see what is happening in effect. The SEH is a standard energy harvester, and the SSHI is a synchronized switch harvester on inductor. And you can see the output power is a little bit higher if you are working with such an electronic system behind the energy harvester. There exist several types of that, and also different types of electronic solutions. Another one is called the synchronized charge extraction, which is again circuitry, and the circuitry is a little bit different to that what I've shown you before. So you have different types of electronics, and these different types of electronics lead to a situation that we can get a little bit more of energy out of the energy harvester. If we are considering the state of the art, then we can say energy harvesters generate very small amounts of energy. The power density ranges typically in a way of about microwatt per cubic centimeter up to milliwatts per cubic centimeter. And in some cases you will find in the literature generations of kilowatt hours, which is completely impossible with normal energy harvesters. And finally, a power adjustment is required very often, and this causes higher costs. So I will come to some industrial solutions. Typical industrial solutions for energy harvesting are energy floors. Energy floors is producing something like that. You have a floor, and on the ground you have some people stepping on the ground, and due to that some energy will be harvested. Or they are using that one, that you have a car which is driving across the floor, and then the energy will be generated by this movement. Nevertheless, the conversion, which is used over here, which is used over here is a magneto-electric conversion, and the conversion principle is shown over here. And you can see you have a movement of the floor up and down, and underneath there is construction, and the generator will generate the electricity like a bike generator, because